Hey guys, welcome back to a new video. So in this session, we're going to be solving exercises on how to use volume integrals, so triple integrals, to calculate the volume of arbitrary three-dimensional figures. It is a direct follow-up on my video on surface integrals, where we used double integrals to calculate the surface of arbitrary two-dimensional figures. In particular, in this video, we will be calculating the volume of a cube, a pyramid, a cylinder, a cone, and to end of a sphere. Now, of course, there are general formulas for each of these shapes, but we will be calculating these volumes using a general method of volume integrals, so that you can apply this method for other figures that do not have general formulas for their volume. The timestamps of each of these figures can be found in the comment section below, where you can also ask any question you might have. If you learned something, don't forget to give this video a thumbs up. It helps out tremendously. And with that out of the way, let's get into the first exercise. Let's now go to the first exercise where we want to calculate the volume of a simple cube. We know that each side of this cube has the same length, and let's denote it as A. The first thing that we want to do if we want to calculate the volume of this cube using triple integrals is to choose a coordinate system and then draw it. For a cube, the most evident choice is of course the Cartesian coordinate system, and put its axis along the sides of this cube. So we draw an x, a y, and a z axis as a first step to calculate this volume. And because the side of this cube is of length a, we know that these points will all be a on their corresponding coordinate axis. If we want to use volume integrals to calculate this volume, then we first remind ourselves what an integral exactly is. Let's say, for instance, that we want to determine the entire length of the y-axis, meaning this entire length. We can denote this by the integral from minus infinity to plus infinity, and what we integrate is the infinitesimal element along the y direction, dy. And if we calculate this integral, then we would get the entirety of the y-axis. And of course, this is infinity, however, it's the ID that counts here. Because the same notion of integrating the infinitesimal element from minus infinity to plus infinity to get the entire thing can be done for volumes as well. Let's consider the infinitesimal volume element. This would be in Cartesian coordinates a cube. And what are the sides of this cube? Well, in the y direction, it is of course dy, the infinitesimal element in the y direction. In the x direction, we have of course the side dx, which is the infinitesimal element in the x direction. And then the sides that are left are of course the sides in the z direction, which have the length, the infinitesimal element in the z direction. And it is this volume right here that we will call the infinitesimal volume element. And in the same fashion as we did in one dimension, we can write that the entire volume of space is equal to the integral over this volume element over the entirety of space. And the single integral over the infinitesimal volume element is of course a triple integral over all of the infinitesimal elements in each dimension, because we know that dv is equal to dx times dy times dz. And it is in this sense that a volume integral is actually a three-dimensional integral or a triple integral. And as I said, if you want to denote the entirety of three-dimensional space, so R3, we calculate each of these three integrals from minus infinity to plus infinity, which amounts of course to integrating each coordinate axis from minus to plus infinity. Knowing this, how do we now not calculate the volume of the entire space, but the volume of our cube itself? Well, we know that this is of course the integral over the volume element, the infinitesimal volume element. And as we saw, we can write this as being three integrals, one over dx, one over dy, and one integral over dz. And now we come to the point that really determines the volume of this cube, because we see on our figure that if we want to calculate the volume not of the entire space but only from this cube, we integrate, for example, x from 0 all the way to a and not to infinity. So we know that the boundaries of the x integral will be from 0 to a. And the same can be done for the boundary in the y direction, because we also integrate from 0 to a. So this also becomes an integral from 0 to a. And of course, the same thing can be done for the z direction, where we also integrate from 0 to a. And we thus see that it is the boundaries of this triple integral that will determine the volume of the figure that we are looking at. And at this point, we can simply calculate these three integrals to get the volume of our cube with a side length of a. For the x integral, we simply have x filled in its boundaries 0 and a. And of course, we have the same for our y integral, which goes from 0 to a. And we have the same for our z integral, which becomes z filled in its boundaries 0 and a. If we calculate this, we simply get a minus 0 for the first integral, a minus 0 for the second, and a minus 0 for the third integral. And this very evidently becomes a to the power of 3. And there we have it. We have our volume of our cube with side a. And this result doesn't surprise us at all, because we know that the volume of a cube with side a is simply a cubed. The first step again is to think about a coordinate system. And for a pyramid, the system that is most suitable is again the Cartesian coordinate system. So we draw our x, our y, and our z axis. And we draw the coordinate system in such a way that the origin of our coordinate system is exactly in the middle of the square base of our pyramid. The sides of our pyramid we denote as b. And since we are dealing with a square base, both sides of the square base are length b. The height of the pyramid we denote as h. And at this point we can start thinking about how to calculate this volume. Again, we know that in Cartesian coordinates, what we do is we integrate over an infinitesimal volume element. This volume element has sides dy, dx, and dz. This means that the volume over the entire space is simply the integral over dv, which becomes a triple integral over dx, dy, and dz. And we saw in the previous exercise that what matters here to calculate the volume of the figure that we're looking at are the boundaries of these three integrals. And it is here that the most difficult part of each exercise lies. In the previous exercise where we calculated the volume of a cube, these boundaries were all fixed. They all simply went from 0 to a. However, here we see that we have some difficulty, because let's consider the integration over y, which is this distance, and over x, which is this distance. However, here we see that we run into some difficulties. We see that, for instance, the integration over y when z is equal to 0 is from simply minus b over 2 to plus b over 2. And the same goes for the integration over x, which is also from minus b over 2 to b over 2. However, we see that when we integrate z from 0 to h, so the base of the pyramid to the top of the pyramid, that the boundaries over which we integrate x and y actually decrease. So these boundaries are not 0. And at the top, these boundaries just vanish at all because there is no distance to integrate over. This is what we mean when we say that the boundaries are not fixed anymore. Whereas for the cube, it was just always from 0 to a. Here we see that the boundaries for x and for y actually decrease when we integrate over z. So when z increases, the boundaries of the x and y integration decreases. So how do we solve this issue? Well, let's first think of how we will integrate this volume. And we're going to calculate the volume of this pyramid by stacking surfaces. And which surfaces do we mean? Well, the cross sections that are all squares. This means that when we integrate over z, we are stacking squares. And by stacking these squares from the base to the top of the pyramid, we will get the volume. So let's start with these areas that we're going to stack as we integrate from 0 to h over the z-axis. We know that at the base, so when z is equal to 0, this area is simply b squared. because we know that the base has a length of b and it is a square, so it's simply the surface of a square. However, this is only the case when z is equal to 0, because as z increases, these surfaces shrink. And all the way up to where z is equal to h, which is the top of the pyramid, we know that the surface is equal to 0. Now, going from these particular cases to a more general case, we see that the surface of such a cross-section, so whether it be this one or any other one, is simply the distance in the x direction times the distance in the y direction. And why does x and y then have a factor of 2 in front? Well, it's because we chose the origin of our coordinate system to be in the middle of our square. This means that half of the square's side always lies in the negative part of our coordinate axis. This means that the surface of each cross-section at each height is simply 4 times x times y. And because we're dealing with a pyramid with a square base, this simply becomes 4 times y squared, or 4 times x squared. Either way, x is equal to y. From this we see that the surface of these cross-sections is evidently a function of y. As y increases, the surface increases, and as y decreases, the surface decreases. Let's now write our strategy of calculating the volume of this pyramid by stacking these cross-section as an integral. So know that our volume is simply equal to the triple integral over dx, dy, and dz. However, we now chose that dx and dy we would combine to be dA, so an infinitesimal surface element. This means that we are reducing our triple integral to a double integral. We have dA and we are still integrating over dz. This simply means that we integrate over dz from 0 to h, and at each point of z we are integrating the cross-section at that point. Now, what are the boundaries of this dA, this surface element? Well, simply we integrate from 0 to this a of y. And this a of y is simply the surface of each cross-section at that specific point of z. This means that we can still rewrite this integral as a single integral. So we integrate from 0 to h over the z-axis, and along the way, at each z, we calculate this area a of y, dz. Now you might say that we simply bring this a outside of the integral because it is dependent on y and not on z, so it's considered a constant. But that would be a mistake. Now, why is this a mistake? Because we see that this coordinate y that we use to calculate this surface actually decreases when z increases. So what we're actually saying is that y is a function of z, because as z increases, this distance y actually decreases. And therefore, we know that a is actually a function of z via y. And that's why we cannot bring a outside of this integral, because a evidently depends on z. This is also very clear from seeing that these surfaces are, of course, dependent on z. Which brings us to the next part, which is to see how actually y depends on z. And to do this, we will look at a cross-section of our pyramid. Let's say that we are looking at our pyramid from the x-axis. This means that we will actually see two axes. We will see a z-axis pointing upward and a y-axis pointing in the right direction. So this is what we will see if we look at our axis from the x direction. And if we look at our pyramid from this side of x, then we see, of course, that this pyramid is simply a triangle, a two-dimensional figure. We know that this is the origin, this will be b over 2, this will of course be minus b over 2, and this will be h. And what we want to know from looking at our pyramid from this side is how y depends on z. Because we know if we want to calculate these surfaces that we need to calculate our volume, this cross-section, then we always integrate from 0 to y. And we see that this y actually decreases each time z increases. And what we now want to do is to calculate how exactly y increases or decreases as z increases. Well, we simply see that this is actually represented by this curve right here. And we see that this curve is actually just a linear function. And we know how to get the function prescription of a linear function. So what is the function describing this linear descending curve? Well, we know that z is equal to minus h divided by b over 2 times y. And this term right here is the slope of this curve. We see that we are descending h when we are going b over 2 in the y direction. And of course, we add to this the value that our curve crosses the z-axis. As a quick check, we can see that if y is equal to 0, we get z is equal to h, and this is correct. And the other check, when y is equal to b over 2, we get that these two terms cancel out and we get minus h plus h, which is of course 0. So at y is equal to b over 2, which is this point, z is equal to 0 and it checks out. This means that we have a linear function that describes how z changes when y changes. However, we want to know how y changes when z changes. So we can simply rewrite this formula to get y is equal to minus b over 2h times z plus b over 2. And this is exactly the formula that we needed, because at this point we see how y changes when z changes. And because we now know how y changes when z changes, we know how a changes when z changes. And this we need to calculate this integral over dz in order to get our volume. So this is what we are going to do right now. We know that our volume is equal to the integral from 0 to h of this cross section, which is dependent on y, which is dependent on z, dz. And because we now know that a was equal to 4 times y squared, simply the surface of a square, we know that this will be equal to 4 times, and now fill in this thing for y, so this becomes minus b over 2h times z plus b over 2, and we have to square this. And this will be our function a of z, because we see that this is now dependent on z. And what this actually says is how the surface of these cross sections, which we had right here, how does this surface of these cross sections change when we're changing z? And now we can simply calculate this integral. So this simply becomes equal to the integral from 0 to h of 4 multiplied with minus b over 2h times z plus b over 2 squared dz. And this is now a simple one-dimensional integral which we can solve. We can first rewrite this by putting these b over 2 outside of these brackets. And don't forget that we need to square this. So what we get is, we get b squared over 4 times 4, which is this 4 that we also put outside of the integral. And we have the integral from 0 to h of the following, minus 1 over h times z plus 1 dz. And what we now do is a very simple substitution. We see that this force cancels out. So we have b squared multiplied with an integral where we are performing a substitution. So we have minus 1 over h times z plus 1. And now we want to have the same in our differential. So minus 1 over h times z plus 1. This plus 1 doesn't matter because in a differential we can always add or subtract any constant numbers. However, we need to compensate for this minus 1 over h. And we compensate by this by simply multiplying by minus h, because then this simply just becomes z again. Of course, we need to adapt our boundaries, because if z is equal to 0, then minus 1 over h times z plus 1 simply becomes 1. If z is equal to h, then we get minus 1 over h times h, which is minus 1, plus 1 is equal to 0. So these are our two new boundaries. This can then be calculated. We have b squared multiplied by minus h, which is this constant that we put outside of the integral, multiplied with the integral from 1 to 0 of u du. And I see that I have forgotten a square in all of these, but that doesn't matter just until now. So I can correct it at this point. And we see, of course, that u is equal to minus 1 over h times z plus 1. And this can be very easily calculated because this is a very standard integral. We have b squared multiplied by h, and this minus sign we put in front, multiplied with the integral of u squared, which becomes 1 over 3 u to the power of 3, filled in the boundaries 0 and 1. This simply becomes minus b squared times h divided by 3 times minus 1, which is of course b squared times h divided by 3. And this is our final answer for the volume. And we know that this is correct because there is a standard formula for the volume of a pyramid with a square base. It's simply the base squared times the height divided by 3. And this is how we used volume integrals to calculate the volume of this pyramid. Let's now go to a much easier exercise where we want to calculate the volume of a cylinder. The cylinder has a height of capital H and a radius of capital R. And at this point we need to think about what coordinate system we are going to use. And for a cylinder, it's quite self-evident that we will use cylindrical coordinates. And to show how these coordinates look like, let me first draw the axis of a simple Cartesian coordinate system. So if the x-axis and the y-axis and the z-axis goes straight up. And again, the origin of this coordinate system is at the middle of the base circle. What are now the cylindrical coordinates? Well, we have one coordinate, which will be the h coordinate, which is basically the z coordinate and measures the height of the cylinder. The other coordinate is the radial coordinate, which is basically just the perpendicular distance from this h coordinate. And then the last coordinate is the angle coordinate, which measures the angle between the y-axis and the point that we're dealing with. Therefore, a point will always be characterized by a radius, an angle, and a height. Now, because we are working in cylindrical coordinates, the infinitesimal volume element that we needed to calculate the volume integral will be different from the Cartesian coordinates. In Cartesian coordinates, we simply had that dv is equal to dx times dy times dz. However, x, y, and z are not the coordinate systems that we're working with. In this case, we're working with r, theta, and h. And whereas in Cartesian coordinates, the infinitesimal volume element was a simple cube, here it will not be a cube, but something different. And this is what we're going to look at first right now. Let's consider a cylinder again. This would be the h-axis and the r-axis would be something like this. Now, what is the infinitesimal volume element? It will basically be a volume element where the sides are given by these three coordinates. So what will be the volume element of a cylinder? Well, it will look something like this. The surface corresponds to the surface of a cylinder. And then in the radial direction, it will also have a depth. So this will be the volume element for a cylinder. So what will be the dimensions of this infinitesimal volume element? We know that in the h direction, right here, will obviously be dh. In the radial direction, which is this direction, will be dr because it's in the radial direction. And then these distances here, these are a bit special because we see that they will change depending on how far from the middle of the cylinder you are. So this will not simply be d theta, however, it will be r times d theta, because this r takes into account that this distance will become larger and larger the further away you are from the middle of this cylinder. This means that dv in this case becomes r multiplied by dr, dh, d theta, which is notably different from simply dx, dy, or dz. It's this extra r here that makes all difference. Knowing this, we can now actually calculate the volume of our cylinder. We know that the volume of our cylinder is simply the volume integral over the infinitesimal volume element. We know that this infinitesimal volume element breaks down into three different elements. We have r dr, dh, and d theta. And what we now need to find are, of course, the boundaries of these integrals. From R, we integrate from 0 to capital R, namely from the center of the cylinder all the way to its surface. For H, we also integrate from 0, which is the origin, all the way to the height of the cylinder, so capital H. And for theta, we of course integrate over the entire circle, which means the entire circle, so from 0 to 2 pi. And this will be the three integrals that we have to calculate. So we have to calculate from 0 to capital R, r dr, multiply this with the integral from 0 to capital H, dh, and multiply this with the integral from 0 to 2 pi of d theta, which of course becomes 1/2 times r squared filled in the boundaries 0 and capital R, multiplied by h filled in its zeros, and multiplied with theta filled in its boundaries. This becomes equal to 1/2 times capital R squared, multiplied with h, multiplied with 2 pi. And what we see, because we can cancel these two 2's away, so we get r squared times pi times h. And this is indeed the volume of a cylinder that we know. We simply multiply the surface of the circle that makes up the base of the cylinder, and we multiply this with the height of the cylinder. Let's now go to the next exercise where we want to calculate the volume of a cone. So let's draw our cone, and our cone has a radius capital R and a height of capital H. What we are again going to do is we're going to stack surfaces while we are integrating over the H component. So we see that these surfaces will get smaller and smaller as we increase H. So it is these surfaces that we will calculate and add to each other every time we advance in the H direction. And again, we see that this surface A is evidently dependent on H, because each time we increase H, this surface diminishes. We know also that this surface is simply the surface of a circle, and the surface of a circle is simply pi times r squared, and r in this case is the radial coordinate, the distance from the center of the cone. So what we're actually saying when A is dependent on H is that we're saying that R is dependent on H, because we see that this radius of each of these circles depends on H. And how exactly the R coordinate decreases with the H coordinate is given by this function right here, which we again identify as a linear function. And this linear function will give us an expression for the H coordinate. So H is simply equal to minus capital H divided by R over 2. And why is this? Well, this is the slope. And because if we increase the R with capital R over 2, we see that the H coordinate will have decreased capital H. And this will give us the slope. And we multiply this with R, our new variable. And of course, we have to add to this capital H. Again, as a check, we see that if R is equal to 0, that H is equal to capital H, and that checks out. If R is equal to R over 2, which is this point, then H is indeed 0. Because if this is equal to R over 2, these two cancel out and we have minus H plus H, which is indeed 0. We now have H as a function of R. However, we want it the other way around. We want R as a function of H, because then we can write A, the surface of each cross-section, as a function of R, but now as a function of H. So we need to rewrite this equation. Rearranging it, we get R is equal to H minus capital H, divided by capital H multiplied by R divided by 2, but now with a minus sign in front of it, which can then of course be again rewritten as minus R divided by 2H times H plus R divided by 2. And this is exactly the equation that we need, because at this point we have R as a function of H. And therefore, we now know how these cross sections scale when we increase H. So now we can calculate the volume of our cone, which is simply the volume integral over the infinitesimal volume element. However, we know now that this integral splits up into two integrals, namely one over the infinitesimal surface element, so over these cross sections, and we add all of these cross sections in the h direction. H we integrate from 0 to capital H, simply from the base to the top of the cone, and the surface we integrate from 0 to this variable surface, which is a function of h. This can then be rewritten as a single integral from 0 to capital H of this variable surface, which is dependent on h, dh. And this is a simple integral that we can now solve. So we get the integral from 0 to capital H. And now filling in the fact that a was equal to pi times r squared, but we have now a function for r as a function of h, we can write the following. So we have pi times r squared, which simply becomes minus 2 over 2 capital H times h, plus capital R divided by 2 squared dh. And this is an integral that we can now simply compute by a simple substitution. But before we do that, let's first put these r over 2's outside of the square and outside of the integral together with this pi. So we get that this is equal to pi multiplied by r squared divided by 4 of the integral from 0 to capital H, from the base of the cone to the top of the cone, of the following. Minus 1 over capital H times h plus 1 squared dh. And this we can simply solve using substitution. So we have pi multiplied by r squared divided by 4 of the integral of the following. So we have minus 1 over capital H times h plus 1 squared times d of minus 1 over capital H times h plus 1. But of course we need to compensate for this minus 1 over capital H, which we do by multiplying by minus h. And the boundaries of course also need to be adapted. So if small h is 0, then we see that our new integration variable is simply 1. If small h is equal to capital H, then we see that we have here minus 1, and then we add 1, so that our boundary becomes 0. And this is very similar to the exercise on the pyramid that we did before. So we get pi multiplied with r squared divided by 4 multiplied with minus capital H, which is this compensation factor, multiplied by the integral from 1 to 0 of u squared du. And this can very easily be calculated as being pi times r squared divided by 4 times minus capital H multiplied by 1 over 3 times minus 1. And this simply becomes pi times r squared over 4 multiplied by capital H times 1 over 3. And at this point, I realized an error. In the entire calculation, I used the radius of the base circle as being r over 2. However, instead, I should have just used r. And therefore, this 4 here is actually a mistake, and this simply becomes r squared. And because I've realized this error, we again get the right result, because we get pi times r squared multiplied with h divided by 3. And this is indeed the volume of a cone with a radius r and a height h. Let's now go to the final exercise where we want to calculate the volume of a sphere. And the first step again is to think about coordinates. And since we're dealing with a sphere here, let's just take spherical coordinates to solve this exercise. And before we dive into it, let me first simply draw the spherical coordinates just to avoid any confusion and so that we are all on the same page. And of course you saw me drawing Cartesian coordinates here, but this is simply to show what the spherical coordinates actually are. Let's say that we have a point right here and we want to describe it in spherical coordinates. The first coordinate is of course the radial coordinate. It's the distance from the origin that our point is. So this we call r. For the second component, we project our vector r to the xy plane. In this case, it will be this point right here. So this will be the place of our point if it's projected along the z direction onto the xy plane. Now the projection of our r vector on the xy plane makes an angle with the x-axis. And this angle will be phi and will be our first angle coordinate of our spherical coordinates. And then the last coordinate is simply the angle that our vector r makes with the z-axis. And this we will call theta. And it is in this way that our point is described by r, phi, and theta. So one distant from the origin and then two angles to denote our point in three-dimensional space. So let's now indeed consider a sphere with a radius capital R. Now, what is the volume of this sphere and how can we get it by using volume integrals? Again, the step that we still need to do is to get the volume element. We know that in Cartesian coordinates, this volume element was simply dx, dy, dz, because it was simply an infinitesimal cube. We know that in cylindrical coordinates, our volume element becomes r dr, d theta, dh. And now we want to know what the volume element is in spherical coordinates. I will make a separate video where I exactly calculate what this volume element is. However, here I simply want to reiterate how this approximately works. So let's again draw our sphere right here, like this. And let's now consider what the infinitesimal volume element of this sphere is. The surface of this volume element will be in the surface of the sphere itself. And then the depth of this volume element will be in the radial direction. And this is how we will get a spherical volume element. However, what are now the dimensions of this volume element? Well, we know that in the depth, in the radial direction, it will simply be dr. In this direction, it will be r times sine of theta times d phi. And in the final direction, it will be r times d theta. And if this is not entirely clear how or why this is true, I refer you to my other dedicated video to calculating this specific surface element. So we know that dv is simply equal to r squared times the sine of theta times d phi d theta dr. And this is the surface element that we will need in order to calculate the volume of this sphere. So again, we have that the volume of our sphere is equal to the integral over the volume element. This basically becomes three integrals and our volume element becomes r squared times the sine of theta, d theta, dr, and d phi. Now, what are the boundaries that will determine the volume of our sphere? We have for the r integral that we integrate from 0 to capital R. So simply from the middle of our sphere to the outer boundary of our sphere. And we have r squared dr. For the angle with the z-axis, we integrate from 0 to pi. And we have sine of theta d theta. And then for the angle with the y-axis, we integrate all the way around from 0 to 2 pi d phi. And these integrals we can now very easily calculate. We have 1 over 3 times r to the power of 3 filled in its boundaries. We multiply this with minus the cosine of theta filled in the boundaries 0 and pi. And we multiply this with phi filled in the boundaries 0 and 2 pi. And this becomes 1 over 3 times capital R to the power of 3. We multiply this with the minus cosine of pi, which is plus 1, and minus the cosine of 0 is minus 1, but we have to subtract it. So we get plus 1, and we multiply this with 2 pi. And we see that we indeed get 4 times pi times r cubed divided by 3. And this is indeed the volume of a sphere with a radius capital R. And this brings us to the end of this long video. And if you're still with me, I'm very proud of you. If you learned something or you appreciated the effort that went into it, give this video a thumbs up. If you want to get notified by future releases, consider subscribing. And with that, I see you guys in the next one. Bye.